Okay, so let's have a look at a nice way to understand why the derivative of sine is cos and why the derivative of cos is the negative sine. And we're going to use a nice argument from mechanics here. So hopefully you'll find this sort of simple and intuitive. So what's quite nice about this compared to other derivations for how to differentiate sine and cos is that here you don't need to use any angle addition formulas, you don't need to use any small angle approximations. We also don't need to go into a power series expansion kind of definition of sine and cos. So it's all quite nice and intuitive. You can think of them in terms of triangles and circles. So let's just get started then. So what's the setup? So basically you're running anti-clockwise at unit speed around a unit circle. So you can say the radius is 1 metre, you're running at 1 metre per second, the units don't really matter. And for convenience we'll say that you start at this point down here where x is 1 and y is 0. So first thing we're going to look at is where are you at time t? So let's say you've been travelling for t seconds, maybe you've not gone very far, and you've ended up at this point here. Now, we actually know that you're running at 1 metre per second, so in t seconds you'll run t metres. And because we're running around this unit circle, this means that the arc length here, the distance you've travelled, is actually going to be t. And this is particularly nice because then we can draw in a little sector like this, and because we're working with radians we'll be able to work out this angle here. So we know that the arc length here is t, so we actually know that the arc length is equal to the angle multiplied by the radius. And here, because we've got a unit circle, you know that the radius is just 1, so you've got 1 unit here, 1 metre. So the radius, this is equal to 1, the arc length is equal to t, and this means that your angle is equal to t. So this is really nice. So we can label this with a t here for this angle. And then this is really useful because now I can actually work out our position in terms of our x and y coordinates of where are we at time t using this little right angled triangle. So let me just draw this out again for us. So you've got a right angle, you've got a t here for this angle, and then your hypotenuse is 1. So this means that your length along here is cos of t, your height here is sine of t. And what this means is we can actually write now, therefore, and I'll write it as a position vector, which just describes where you are. So your position vector at time t is, so where are you? Your x coordinate is cos t. I'll write this as a column vector, so just in the top entry this is your x coordinate, and then sine t is your height, your y coordinate, so cos t, sine t at time t. Of course here we've only really shown this for values of t between 0 and pi over 2. But this argument you can extend this further round, so for t greater than pi over 2, you can actually, if you go beyond 2 pi, you loop back round, you can show that your position vector will still be given by cos t sine t, even for t bigger than 2 pi, and also for t negative. So say if you're interested, say you've always been running at this unit speed around the unit circle, maybe you start off, your starting point here is t is 0, maybe if you want to look what happened 5 seconds before your starting point, so you're over here, and if you work out cos of -5, sine of -5 radians, then you will get the appropriate point there. So now that we've found the position vector, let's have a go at working out the velocity vector to describe our motion around this circle. So let's say we've gone for t seconds, we're at this point here, so we know that we've got an angle of t here, and this arc length is t. And what we're interested in now is actually our velocity, which we think we're running around this circle anti-clockwise. The direction in which we're travelling is always going to be a tangent to this circle. So this is our velocity vector, is going to be in this direction, and we know that we're running at unit speed 1 metre per second, so you know that the speed is 1, And because we also know the direction in which we're travelling, we can work this out from knowing this angle t. This is enough to help us work out what are our x and y components of our velocity vector here. Okay, so what I'll do is drawing, if I extend this vertical line down here, we've got a nice right angle triangle again. So we've got t and then we've got a right angle. So this one is pi over 2 minus t for this angle in here. Then you also know that the radius of a circle, this always meets the tangent at 90 degrees. So you've got a 90-degree angle here, and more importantly, you've got a 90-degree angle here. So actually, you've got this pi over 2 minus t, or your 90 degrees minus t, and that means that this angle here also has to be t. And then, as if I just draw out again, you've got your vertical and you've got your tangent here. You know that you've got an angle of t here, so you've actually got a vertically opposite angle at the top, which has to be equal, so this is also equal to t. So let me label that on here now. So it means this angle here has to be t. And then it turns out this is going to be enough to help us work out the horizontal and vertical components of our velocity. So let me copy out this little bit of the picture here again. So we've got our horizontal, our vertical components describing our motion. And once again, we've actually got a nice right angle triangle going on here. You know the hypotenuse is 1, and we know that this angle here is t, so this is our shaded angle in the diagram. So we know that this length here, which tells us the x component of our velocity vector, we know that that length has to be sine t. And we know that this length, so the side of our velocity in the y direction, our vertical component is cos t. So what does that tell us? Well, if you imagine we're travelling around, you'll notice that our x direction, we're travelling with sort of a speed of sine t at time t, but we're actually going in the negative x direction. So we can say the velocity at time t, first of all, the x component of this is actually not going to be sine t, it's going to be negative sine t. And then in the y direction we're travelling with a speed of cos t. So this gives us our y component here. So the velocity at time t given by minus sine t and cos t. But this is actually really useful now because you know that your position vector is given by cos t in the x direction, sine t in the y direction, and you know that your velocity then is minus sine t cos t. Well, what is the velocity? All the velocity means is that's just the rate of change of your position. So we can actually say then, if you think what would happen if we differentiate this with respect to t, so you differentiate your position with respect to t. So of course when you're differentiating a vector, all you do is differentiate each component separately. But then we know the derivative of cos t sine t with respect to t, this is our derivative of our position vector, that's just the same thing as the velocity vector. So we actually know that this is equal to minus sine t cos t. And then this is really nice because now if you look at your x components, you've shown that d by dt of cos t gives you negative sine t, and you've shown that d by dt of sine t gives you cos t. And of course we've only really shown this in this one quadrant, but you can, as before, you can extend this argument to apply for t greater than pi over 2, for t greater than 2 pi, or even for negative t. But what's really nice about this is that you can understand it, and hopefully it's nice and intuitive using the mechanics style argument.